Hi, my name is John Schultz. I'm from Compass Technology Group, which is a small company in Alpharetta, Georgia, in the USA. Today we're going to talk about some free space material measurement techniques that we work on at our company. And in particular, we've worked on a couple of different correction methodologies to improve the sensitivity, in particular for measuring low loss materials. So to begin, let me first describe a little bit about our broadband free space methods. Now these are methods that either use some sort of focusing elements, and in our case that means lenses, or they're near field spot probes, which we use to measure transmission and or reflection of materials. And then using some physics, we can take that transmission or reflection coefficient and determine the dielectric or magnetic properties. So we have pictured here a couple of examples. On the top right, you'll see a focus beam system, which includes a network analyzer, some frequency extenders, and a pair of lenses. And those lenses help provide a nice, well-controlled beam going through our sample, which is placed in the middle. On the lower right, you'll see an example of a spot probe fixture. So those spot probes are mounted so that they're on either side of an unknown sample, and we can use that system to measure transmission or reflection of the material, and again use the same sort of inversion physics to determine from transmission and reflection what the magnetic and dielectric properties are. Now these methods have some advantages. They can handle lossy materials. There's no real thickness restrictions on our samples. Another advantage is what you see on the lower left. In that case, we have a focus beam system, in this case with larger lenses that allow us to go down to 2 gigahertz. And inserted in the middle of that is an oven. And that oven allows us to heat samples up. And so we can measure materials fairly easily in these free space broadband methods at temperature, either high or low temperatures. So those advantages are nice. But there's an Achilles heel. These free space methods usually suffer from having low sensitivity to measuring low loss tangents. And this is in comparison to other methods such as resonant fixtures. So before I get into the sensitivity improvements that we talk about later in the paper, let me first give you a quick overview of calibration and inversion that we use for dielectric measurements. So calibration, unlike a waveguide, in free space the beam diverges. And so that makes it difficult to use the conventional waveguide type of calibration, such as TRL or some combination of shorts and opens and loads and so forth. Instead, we keep it simple. We use just a response or response and isolation calibration. In the case of a transmission measurement that we're doing here, that'll be just a simple clear sight measurement. And then we combine that with time domain gating. And the key about time domain gating is that it helps us to eliminate the multipath errors, from reflections at different, junctions, the horn antenna, the lens, the ported network analyzer, that would otherwise be taken care of by a more advanced calibration method. So in that case, we take lots of data over a range of frequencies, and then we can use Fourier transform techniques to transform into time domain, put windows around the data that we know is relevant, and zero out the non-relevant reflections, and then transform back into frequency domain. So once we've calibrated, then we use an iterative method to calculate our permittivity. And there are sort of standard techniques such as a Newton's iteration, and that's what we're using here. And basically it helps us to solve the transcendental equation that relates the, in this case, S21 transmission coefficient to the real and imaginary permittivity. So now the question is, what sort of approximations are we making that then create systematic error? So in the case of a free space illumination, we assume that we're illuminating with an ideal plane wave. The reality, though, is that a plane wave is infinite in extent, and we have a finite size sample, and in fact we want to avoid edge illumination so we don't have edge diffraction effects. And so we actually have either a focused beam or a confined spot that we illuminate on the sample that is no longer an ideal plane wave. You can describe this now as, instead of a single plane wave, as a distribution of different plane waves with different weights and phases, which then add together coherently to create this sort of confined spot. You can also describe this using the physics of Gaussian beam optics, and you can describe really the shape of the amplitude taper in the spot to have this sort of Gaussian shape, and it has a characteristic distribution of plane waves centered around the normal incidence plane wave K0. So the effect of a non-ideal plane wave is most severe in a system such as what we have pictured here, our tabletop spot probe based system. The spot probes don't focus, rather the beam just diverges from the end of the probe, and because of that we get some additional bias in the transmission coefficient that we measure. So the plot on the top right shows the transmission coefficient, which we describe as S21, and this is the amplitude in dB, for a high density polyethylene sample as a function of frequency. And you'll see sort of the characteristic wiggle of constructive and destructive interference between the front and back surfaces of the sample. But you'll also notice that, and I have it circled here, that the peak of the transmission coefficient goes above 0 dB. And of course that's non-physical, that would be gain, and this is a passive material. We should not be adding in any additional energy. And so that apparent gain, which is on the order of 1/10 of a dB, is due to this non-ideal plane wave nature of the system. It's sort of a focusing effect in essence, where the sample itself sort of takes the energy that's coming out of the probe and kind of semi-focuses it so that more energy ends up going into the receiver side. And because of that, we can apply an analytical correction based on simple Snell's law kind of derivation, which we'll show you here in a minute. This slide shows a cartoon on the right that describes the effect of the beam shift that I just discussed. So here we have energy from a diverging spot probe, which is sort of shaded in green, starts on the left side and moves to the right, and it's passing through a finite thickness sample with thickness T, which is colored in yellow. And I show sort of pointing vectors, the arrows, which show you the orientation of, say, plane waves in our distribution of plane waves. And as you can see, because of the higher dielectric constant of the material versus air, you refract energy when it goes into the sample. And that refraction has the equivalent effect of essentially shifting the beam towards the receiver side. And so that refraction, of course, is directly related to Snell's law. And if we make a small angle approximation, which essentially assumes that we have a fairly directive beam, we can calculate the amount of that beam shift. And that equation on the bottom left relates the beam shift, which is delta D, to proportional to the thickness of the sample. And it's also related to the inverse of the square of the dielectric constant as well. So now with this beam shift, we can then go and apply a correction. The second piece of information we need to apply our beam shift correction is knowledge about what the space loss is. In particular, as we move the transmit and the receiver closer or farther away from each other, there's going to be a variation in the transmission coefficient between them. And so we have to either experimentally or with computational models determine the relationship between the distance between the transmit and receive and the actual transmission coefficient between them. When we have that extra piece of information combined with an estimate of what the beam shift actually is for a given sample, we can then combine those to apply an actual correction. So the plot on the right shows that same high-density polyethylene sample that I showed a couple slides back, and the thinner black lines show the data that I originally showed you, which was essentially uncorrected. And then after we've applied this beam shift correction, you can see that it accounted for the bias that occurred due to this beam shift effect through the sample. So this beam shift correction is probably the #1 source for bias in spot probe measurements. This correction also applies to focus beam measurements as well. However, the effect is nowhere near as strong as it is for a spot probe, so it's much more important to use it in the case of near-field probes. So as engineers, we're of course never satisfied, and while one correction may be great, adding additional corrections is going to be even better. And so we're going to keep going here and look at a second correction method. This correction, of course, is not as big of a deal as the beam shift correction, but when we're starting to go and measure very low loss materials and really trying to get good accuracy at those low losses, this is an effect that can come into play. So this is what we call a focusing effect. This is actually based on work that Ricard Peterson did as a grad student back at Georgia Tech some years ago, where he derived an expression based on a plane wave expansion of the power transmission through a sample focused or illuminated by a focused beam. And so you can go look up his thesis, and he and Glenn Smith published a number of papers on this effect. And we're going to take advantage of his work, where we have sort of this integral expression that relates the power transmission to the plane wave distribution. And so since we have a Gaussian beam, we know a little bit about how hard we're focusing. We can determine what the exact plane wave distribution is and use that to determine the effect of focusing. To apply this focusing error correction, we essentially numerically solve the above integral, and we incorporate an estimate of the dielectric permittivity of the material under test, which we do know. And then based on this, we can have a second amplitude correction for our S21, our transmission coefficient, based on this focusing error. The plot on the bottom right shows that calculation for a 6.3 millimeter thick high-density polyethylene sheet in our E-band focused beam system. So this is an actual calculation. You'll notice that the differences that we see in the transmission coefficient based on this focusing error correction are on the order of maybe 1/100th of a dB, or maybe a couple hundredths of a dB at most. So it's a very, very small effect. It's typically, in a focused beam system, it's typically 2 to 5 times smaller than the beam shift correction. But again, 2 corrections is better than 1, so we're going to use it. And as we'll show in a little bit, we'll show you some actual data where we show both uncorrected and then corrected. We're going to apply both of these corrections, the focusing error correction as well as the beam shift correction. And that we're going to use that to essentially update our iterative method to get a more accurate dielectric permittivity. So before I show some data, let me quickly summarize what it is we're going to do to correct that data. So this is an overall summary of the correction algorithm, which includes both the beam shift and the focusing. And I should also mention that in the case of the beam shift, I showed you the amplitude correction that happens, but there's also a phase correction that also happens. That is not a huge correction, but it's not zero either. So we're going to apply both the amplitude and phase correction from the beam shift. So essentially we measure S21, that's our transmission coefficient. We first estimate our permittivity by inverting it using the standard methods I talked about way back at the beginning, and that gives us a sort of uncorrected permittivity. And then we use that uncorrected permittivity to calculate the correction factors, both from the beam shift and from the focusing effect. And like I said, the beam shift is going to have both an amplitude, which I showed, as well as a phase effect. And then, of course, we also have the focusing error. We add those corrections back in to our S21, and then we reinvert the permittivity, again, using the standard Newton's method techniques, and that gives us our corrected permittivity. So now I'm going to show you a few slides where we show some canonical samples that we've measured and applied corrections to. So this first example is of some 3 millimeter thick acrylic or polymethyl methacrylate. In this case, we are measuring it in our spot probe system, which you also see pictured here. I have two plots on here. On the left side is the real permittivity or dielectric constant, and on the right side is the loss tangent. And both of these are as a function of frequency. You can see that there's several curves. The thin dashed line is the uncorrected, using the standard inversion method. The thicker blue line is after we've applied the beam shift correction. You'll notice that in the case of the real permittivity, there's not a whole lot of effect from this correction, but there is a significant improvement in the data in terms of the loss tangent on the right. I've also included on these plots some red dots, which are some literature data from Maloney back when he was at NASA back in the late 60s. And you can see that, and these were measured with an interferometer, and you can see that they agree very nicely with our current results. The second example is, instead of a tabletop, is using our focus beam system. A tabletop is a relatively low-cost system. The focus beam is more accurate, of course, more expensive. In this case, we're also measuring a more difficult specimen, a 6.35 millimeter thick piece of fused silica. It's more difficult because of the fact that it's lower loss. I should also point out that at these frequencies, it's about 1.5 wavelengths thick, which is significantly thicker than you could do in a Fabry-Perot interferometer. Again, we have two plots, the real permittivity on the left and the loss tangent on the right, both as a function of frequency. And the uncorrected data in both of these plots is the thin dashed line. The amplitude correction based on both the beam shift and the focusing error is the blue line. And then when we also include the phase correction that comes from the beam shift, that's the full correction line, which is in green on both of these plots. As you can see, that the phase correction does have an effect on the real permittivity. Not a huge one, but not an insignificant one either. And of course, our loss tangent is improved both by the amplitude and the phase correction, as you can see on the right. If you sort of assume that the ripple is sort of our uncertainty or error, and we average through that, then we can sort of conservatively come up with a mean and standard deviation for our measurement, which is kind of showing that our loss tangent sensitivity is on the order of 0002. Well, that concludes my talk. So to summarize, we derived some corrections that we can apply to reduce the bias in broadband free space measurements. And these significantly improve the accuracy both of spot probe measurements as well as focus beam. And of course, these have the advantage of being able to measure thick samples. I also showed you a couple examples where we characterized some low loss materials and demonstrated that we had a sensitivity of about 0002 at E-band for these measurements. Thank you.